So in this video lesson, we're going to have a look at mole ratios and something called stoichiometry. Don't be concerned if you don't know what stoichiometry is yet. It's a fancy word in chemistry, but we're going to learn about what it is through this video lesson. So when we are looking at a balanced reaction, so we're going to look at a reaction. We're going to have a look at this reaction with nitrogen reacting with hydrogen to give us ammonia, which is NH3. Okay, when we look at any reaction ever, because we know how to balance, we want to make sure that all of our reactions are balanced anytime we need to use them. So we are going to balance this out by putting a 3 in here for our hydrogens so that we have 6 hydrogens on the left. And then a 2 in here for our NH3, so we now have 6 hydrogens on the right. And that's going to work for our nitrogens as well, to be 2 nitrogens on the right side and 2 nitrogens on the left side. So the most important thing is to have a balanced reaction. You can't do anything in chemistry if your reaction isn't balanced. And you definitely can't do anything with mole ratios or stoichiometry if you don't have a balanced reaction. Even if you're pretty sure that it's balanced, double check, make sure the reaction is balanced. It is the most important part, because if you do not start with a balanced reaction, all of your calculations will be entirely wrong. Okay, you want to make sure that we start with that balanced reaction. Now, if we talk about this reaction in words, we could say that 1 mole of nitrogen is reacting with 3 moles of hydrogen to produce 2 moles of ammonia. And so those numbers, 1 mole, 3 mole, and 2 mole, those are coming from our balanced reaction. So those are coming from the coefficients in our balanced reaction. So this is called a mole ratio. 1 mole of nitrogen requires 3 moles of hydrogen to produce 2 moles of ammonia. So if we want to write those as just mole ratios, a ratio always has a number and then our little ratio symbol. So a ratio is a number to a number of some kind. Okay, so if we want to write the mole ratio of, let's go with nitrogen to hydrogen, then the mole ratio of nitrogen to hydrogen is going to be 1 to 3. For every 1 mole of nitrogen, we will need 3 moles of hydrogen. If we want to do the mole ratio of, say, hydrogen to our ammonia, then it would be 3 to 2. For every 3 moles of hydrogen, we're going to make 2 moles of ammonia. We could also do nitrogen to ammonia if we wanted, and that one would be 1 to 2. And we could also write our ratios backwards. So if we instead wanted the ratio of hydrogen to nitrogen, then it would be 3 to 1. Okay, and it's all about what you want the ratio of compared to the other substance. So whatever your starting substance is, whatever your ending substance is, but you can decide what that is. You just want to make sure that you're reading questions carefully. For instance, you don't want to say 1 to 3 if you want the ratio of hydrogen to nitrogen, because that's the ratio of nitrogen to hydrogen, and you don't want to flip-flop them. Okay, so those are our mole ratios. Now, if we had a slightly different reaction, so we're going to start with a new reaction here. So we're going to have 2 moles of hydrogen will react with 1 mole of oxygen to make us 2 moles of water. Okay, now in this reaction, if we say wanted the mole ratio for hydrogen to water, that would be 2 to 2. But we can simplify that to 1 to 1. So ratios, just like fractions, should be simplified to their lowest common denominator. Okay, so rather than saying 2 to 2, you would say 1 to 1. All right, now 2 to 2 is not wrong. It's the same as 1 to 1, but you always want to reduce your ratios to the lowest common factor. So they're just like a fraction, right? We wouldn't want to give fractions like 2 over 6. We would say 1 over 3. So we want to reduce to our lowest common factor. All right, now when we're looking, let's just keep this same reaction here. So we have a 2 in front of our hydrogen, a 1 in front of our O2, and then a 2 in front of our H2O. And so we can actually use this mole ratio to convert between moles of one type of substance to moles of a different type of substance. Okay, and so we can use that mole ratio. So, for example, if we start with 3 moles of hydrogen, how much oxygen will we need? Okay, because reactions have to occur in those specific ratios. And so if we start with 3 moles of hydrogen, how much oxygen are we going to need? So when we do this calculation, let's do it in a green. We're going to start with our 3 moles of H2, and we're going to multiply by a conversion factor. Now, this conversion factor is going to be our mole ratio, okay? Very, very important here. What goes on the top, what goes on the bottom. So we want to put moles of hydrogen on the bottom. And since we want to find oxygen, we are going to put moles of oxygen on the top. Now the numbers are the mole ratio. So if we look back at our reaction, the ratio of hydrogen to oxygen is 2 to 1. So for every 2 moles of hydrogen, there's 1 mole of oxygen. And so we're getting a conversion factor of 1 over 2. Okay, and that's specifically because we want to be able to cancel out those moles of hydrogen so that we're going to be left with moles of oxygen. So when we do that, we're going to get 1.5 moles of oxygen. And now, because we're using a number like 3 and we have a very easy ratio of 1 to 2, that makes a lot of sense that we use half as much oxygen because the ratio is 2 to 1. Okay, but the reason we need to be able to use this conversion factor is because what if instead we started with 4.875 moles of hydrogen? Okay, and so that one's a little bit harder to visualize in our head, and so we want to be able to use conversion factors. We use the same conversion factor here because we want to know how much oxygen that's going to take. And so again, we're using that conversion factor so we can cancel out the moles of hydrogen. And so then when we do that math, we do 4.875. We're dividing it by 2. We get 2.438 moles of O2. Okay, and that's just a little bit more difficult to do in our heads. We want to be able to have the math to back us up so that if we started with an odd or weird amount of moles to start with, that we can still find out how many moles of the substance we're looking for. Okay, so we did that mole ratio with the 2 reactants, but you can use the mole ratio with products as well. So if we're using the same reaction still, if we go from, say, let's start with knowing, so we are going to start with, so we want to make 3.75 moles of H2O, and I want to know how much oxygen we'll need to use to create that 3.75 moles of H2O. So we're starting with our 3.75 moles of H2O, and we're going to multiply by a conversion factor. Now, because I want moles of oxygen is going to be on the top. And because I have moles of water is going to be on the bottom. And then I want to include that ratio from my balanced reaction. So from my balanced reaction, 1 mole of oxygen will give me 2 moles of water. So it happens to be the same ratio as oxygen to hydrogen. And again, the reason that we're doing that is we want to make sure that we can cancel out the moles of H2O. So we'll be left with moles of O2. So then we're taking our 3.75, dividing it by 2. We're getting 1.88 moles of O2. So to make 3.75 moles of water, we're going to have to use 1.88 moles of O2. All right, so that's how we use our mole ratio, and that's what stoichiometry is. So stoichiometry is really the use of mole ratios in a balanced reaction to convert amounts of one substance to amounts of a different substance. So with stoichiometry, we're using that mole ratio in our balanced reaction, and we're just using it to convert from how much of one thing in the reaction we have to how much of another substance in a reaction that we need or that we have. Okay, and so that's what stoichiometry is. All right, we're going to move on a little bit further, and we are going to look at a new reaction here. Only this time, we are going to do some more complicated conversions. So the reaction we're going to use is ammonia reacts with oxygen gas to create water and nitrogen monoxide. Okay, so hold on, we're going to get our nitrogen monoxide in there a little better. All right, so one of the first things we want to do is make sure that this reaction is balanced, okay? And so in order to do that, I think I'm going to start with my hydrogens. And if I start by putting a 3 here for my hydrogens, and a 2 here for my hydrogens as well, that's going to give me 6 hydrogens on both sides. But then I need a 2 for my nitrogen over here. But then that's going to put my oxygens out of balance because I'll have 3 oxygens plus another 2. So I'll have 5 on the right, but only 2 on the left. And so instead, I think I'm going to up this 3 to a 6. So then that's going to change both my numbers in front of my NH3 and my NO. So I'm going to have to put a 4 in front of my NH3 to balance out my hydrogens, and then a 4 in front of my NO to balance out my nitrogens. And now I have 10 oxygens on the right, so I can put 10 oxygens on the left by adding a 5. So now we have these coefficients, and now we have a balanced reaction. Again, that is the most important thing when doing these stoichiometry calculations, that we are dealing with a balanced reaction. All right, so in these stoichiometry calculations, we are actually going to learn how to use some calculations that are going to involve having to use 3 conversion factors. Okay, so when we were using the mole ratio, we learned that new conversion factor of the mole ratio. But if you think back in this unit, we also have 2 other conversion factors. We know how to convert from molecules or particles into moles. We also know how to convert from mass into moles, and we can go backwards for both of those as well. So we have multiple conversion factors that we could be using within our stoichiometry. All right. One of the first things that I'm going to do is, because I'm going to use this reaction for a little while, I'm going to write out the molar masses for each of my substances. So I'm just going to add a little table underneath my reaction here to put my molar masses. And they're all going to be in grams per mole. And so I'm going to calculate these from the periodic table. When we're calculating molar mass, we do not include the coefficient. The coefficient is there to balance the reaction. It is not part of the molar mass of the compound. So for NH3, we have 1 nitrogen, which is 14.01, and we have 3 hydrogens that are each 1.01. So we get a molar mass for ammonia of 17.04. For oxygen is going to be the 2 oxygen atoms, so that's 32 grams per mole. Water has a molar mass of 18.02, 2 hydrogens and 1 oxygen. And then nitrogen monoxide has the 1 nitrogen and the 1 oxygen, so it's 30.01. Okay, those are all measured in grams per mole. And again, we get all of those molar masses from the periodic table. Okay, when we're doing stoichiometry calculations, because we're doing a lot of calculations with this reaction, it's sometimes easier just to find the molar masses to start with, then you have them for reference for later. All right, so we are going to do some calculations here, and we are going to start with this first one. So we're going to number them. So our first question, we're going to do how many grams of water are produced if 1.9 moles of ammonia is used. All right, so we're going to start off with that first one here. So we're going to look at water compared to our ammonia. So we're starting with our 1.9 moles of ammonia. Okay, and I want to finish with grams of water. So the first thing that I need to do is I have to use a conversion factor that's going to let me get rid of moles of ammonia. Okay, and so I want moles of ammonia to be on the bottom here. And this is going to be my mole ratio. This is the only conversion factor that allows us to change from moles of one substance to moles of a different substance. And so on the top, I want to put my moles of H2O. And ammonia goes on the bottom because I have ammonia. Water goes on the top because that's what I want. Anytime you're using this mole ratio, you always want to put what you want over what you have. Okay, and so our ratio is going to be 6 moles of water to our 4 moles of ammonia. Now, we could reduce this if we wanted to and make it 3/2, and that'd be fine. But it's also not terrible to use it as just 6/4, just reading it directly from our balanced reaction. Okay, now if we stopped right there, that would get rid of moles of ammonia, but we'd be left with moles of water. But that's not what we want. We want grams of water. So we're going to use another conversion factor here to help us get rid of the moles of water. Okay, and so 1 mole of water is going to be that 18.02 grams of water. And that's going to help us get rid of our moles of H2O. And that's going to leave us with grams of H2O. And so when we do that, we do our 1.9, we times it by 6, divide it by 4, and then multiply by 18.02. So we're getting 51 grams of H2O. Okay, and again, that molar mass always comes from the periodic table. So that's a conversion factor that's always true, right? 18.02 grams for 1 mole of water. Okay, all right, let's try another question. So in this one, I want to know how many grams of oxygen. And again, we're going to use that same reaction. So how many grams of oxygen are required to produce 0.30 moles of H2O? Okay, so in this one, we're looking at how many grams of oxygen. That's what we're trying to find. And we are starting with 0.3 moles of H2O. So we're going to put our starting amount down here, 0.30 moles of H2O. And the first conversion factor we're going to use is going to be our mole ratio, because we want to go from moles of H2O to moles of oxygen. So we're going to put moles of H2O on the bottom because that's what we have. Moles of oxygen on the top because that's what we want. And our ratio of oxygen to H2O, oxygen is 5, H2O is 6. Again, that just comes from our balanced reaction. So that's going to allow us to cancel out moles of H2O. And if we just finished there, that would give us moles of O2. But we want grams of O2. So we want to keep going with another conversion factor. So in this conversion factor, we want to get rid of our moles of O2. So we want grams of O2. Okay, so 1 mole of O2 is our 32.00 grams. And that's just our molar mass. And so that's going to allow us to cancel out our moles of O2, and we'll be left with our grams of O2. So when we do the math there, we're doing our 0.3, multiply by 5, divide by 6, and then multiply by 32. So we're getting 8.0 grams of O2. All right. So in these two questions, we've been using two conversion factors. We've been using the mole ratio conversion factor. And so that's this one, right? Our mole ratio. And then, ratio. There we go. And we've also been using the molar mass conversion factor. So that's this one in yellow. So that's molar mass conversion factor. Okay, now we're going to do 2 more questions, only this time we're going to have to use 3 conversion factors to get from what we have to what we want. Okay, the nice thing about conversion factors is you can use as many in a row as you want to. All right, so we're still working with the same reaction, only in this next question, I want to know how many grams of NO is produced if 12 grams of O2 is used. All right. So we are going to start with our 12 grams of O2, and we want to find how many grams of NO. All right, so we're starting with our 12 grams of O2, and we're going to need to multiply by a conversion factor. This conversion factor, though, is going to have to get rid of our grams of O2. So it's going to have grams of O2 on the bottom. And the only conversion factor we know of that has grams in it is the molar mass conversion factor. And that's going to convert to moles of O2. So 1 mole of O2 is that 32.00 grams. So that's going to allow us to cross out our grams of O2. And we'll be left with moles of O2. But we don't want moles of O2. We want to convert it into nitrogen monoxide. So now we're going to use our mole ratio conversion factor. And so this one is going to have moles of O2 on the bottom because that's what we have, and moles of NO on the top because that's what we want. And the ratio for those two, if we go back up to our reaction here, we have O2 is 5 and NO is 4. So our O2 is going to be 5 and our NO, nitrogen monoxide, is going to be that 4. That's going to allow us to cancel out our moles of O2. And if we just finish there, we'd be left with moles of NO. But we want grams of NO, so we're going to keep going with a conversion factor. And so this next conversion factor, we want to put moles of NO on the bottom and grams of NO on the top. And so 1 mole of the nitrogen monoxide is at 30.01 grams. And that's going to allow us to cancel out our moles of NO. Right? And so that's going to leave us with grams of nitrogen monoxide. So when we do the math here, we're going to do 12 divided by 32. We're going to multiply by 4 and then divide by 5. Then we're multiplying by that 30.01. And so that's going to give us 9.0 grams of nitrogen monoxide. Okay? And so in this scenario, we've now used 3 different conversion factors. So we've used that mole ratio, but we've also used our molar mass conversion factors for our 2 different substances. So at the beginning, because we had the mass of oxygen, we had to use the molar mass conversion factor to get moles of oxygen. Then we used our mole ratio to convert to moles of NO. Then we used our molar mass conversion factor for nitrogen monoxide to convert to mass of nitrogen monoxide. All right, let's do one more that's going to use that 3-step conversion. So this is going to be question number 4. All right, in this one, I'm going to look at how many grams? So how many grams of water are produced when 17.0 grams of ammonia are used? All right, so we are going to start with our 17 grams of ammonia, and we're looking to find how many grams of water that's going to create. So we're starting with our 17.0 grams of ammonia, and we're going to have to multiply by that molar mass conversion factor to get 2 moles of ammonia from grams of ammonia. So 1 mole of ammonia was our 17.04 grams. Okay, and that's going to allow us to cancel out our grams of ammonia. Then we're going to have to use our mole ratio conversion factor. Our moles of ammonia are going to go on the bottom. Moles of water are going to go on the top. And the ratio is 6 waters for every 4 ammonias. Okay, that's going to allow us to cancel out our moles of ammonia. If we finish there, we'd be left with moles of water, but we want grams of water. So we're going to use a 3rd conversion factor. And we know that our 1 mole of water is going to be 18.02 grams of water. And so that's going to allow us to cancel out our moles of water, and we'll be left with grams of water. So then when we do that math, we're doing 17 divided by 17.04, multiply by 6, divide by 4, multiply by 18.02, we get 27.0 grams of H2O. Okay, and so again, we're using those 3 conversion factors in a row. Okay, you can use as many or as few conversion factors as you need to convert your units from what you have into what you want. Okay, if you start with grams and you want to end with grams of something else, you're going to have to use all three of these conversion factors in a row to go from grams of one substance to grams of a different substance. If we start with moles, we can use less conversion factors. Okay, so if we want moles to mass, then we would use just the 2 conversion factors like we did in question 1 or question 2. If we want moles to moles, we can go back and just use the 1 conversion factor. That mole ratio conversion factor will get us from moles of one substance to moles of a different substance. Okay, and so you can use 1 conversion factor depending on the units you're trying to convert between, or 2 conversion factors, or even 3 conversion factors. All right. What you should be working on now is that mole ratio practice worksheet. As well, there's a stoichiometry practice worksheet. There are lots of questions to try with answer keys attached. Please make sure you try as many as you need until you feel like you've actually got the hang of it before you do the check-in and before we work on an assignment next week. All right.